everyone hear me? Fine? Awesome. So, as you can see, my talk is called Perfidious, Make Backdooring Great Again. Here, I'll be introducing you to a possible new technique that could be used to backdoor PE files. But I want you to remember that instead of focusing on the technique itself, you should focus on the bigger picture, which is the tool itself and the library that is being currently developed. So, this is the URL where you can find these slides if you want to download them. Just tinyurl.com. I like reverse engineering and malware analysis, so these are my handles. And that's enough about me. I would like to know what is the demographic of the audience right now. So how many of you are interested in malware analysis, reverse engineering? Okay, awesome. So we are going to talk about those things. Let's get started. So, in order to understand how this library came into development, it's important to know the context in which this particular project came into being, right? So, during the summer of 2019, I started interning at Cybery. At that time, there was nothing I knew, like what I was going to do. I was basically screened for just like malware analysis skills and machine learning skills. After that, my mentor for the project basically told me that he wanted to develop a tool that could be used as a framework to develop new malware samples that use machine learning in order to learn over the current malware sample source code in order to generate new samples that could maybe bypass the endpoint detection systems. Now, when he told me about this project, I had two basic questions. First, where would I be able to find source code for so many malware samples, and how would I develop parsers for all the various languages in which these malware samples are made in? The second question was, is this even legal for me to work on? Because I don't want FBI knocking on my door. So, as fate would have it, after introducing the idea in 15 days or something, he basically left the company and joined another firm. So, I was left with this project to do whatever I wanted to do with on my own. So, there were basically two choices with me. I could idle away my time at Cybery and get paid for it, or I could develop a project which could be a possible step to this project. So that is where Perfidious came into picture, right? So in order to understand what Perfidious does, it is important to know what PE file format looks like and what are the different structures that are present inside a PE file, right? So these are the basic components of a PE file. There is the DOS header, there is DOS stub, then there is a recently discovered structure, say 2015, called rich header. There is the PE signature followed by the NT header, which consists of the file header and the optional header, which points to the data directories, followed by the section header and the actual sections which contain the data of the PE file. Right? We'll go into all these sections in detail. A few things to remember. These are some of the concepts that you need to know in order to understand how addressing works inside PE files. So there is the raw address. Raw address is basically the actual offset at which a particular thing is present inside a PE file. So you can say if the offset is 135, the 135th bit inside the raw file is where that thing is present. Raw address space is basically the actual address space ranging from 0 to the actual file size of the PE file. Virtual address space. So virtual address space usually begins at 400,000 something hexadecimal number. So that is basically the offset from which this particular PE file will be loaded in the memory, and the address space is basically everything ranging from there. So it's important to know the mapping between raw address space and the virtual address space in order to actually map the data structures, because a lot of the offsets present inside a PE file are in RVA format, so we need to convert the RVAs into the raw offsets so that we can actually find those data structures inside the raw file, right? So this is the formula that can be used in order to convert the RVA inside the PE file to a raw address. And so this is the structure of a DOS header. Now it contains a lot of information, but the important ones have been highlighted. E-magic is basically the MZ, you can say the MZ bytes that are present inside a PE file. This basically identifies that this is a PE file. The CSUM is basically the checksum of the PE file itself. and the elf new points to the offset to the extended header. This is where the actual PE file begins from, for most part. The DOS stub. Now, how many of you all participate in Flare on challenges by Fire? So, if you participated in the 2016 challenge of Flare-On, one of the challenges involved a program which was actually a DOS program that was being passed off as a PE file. So, it was not basically able to run on the normal Windows machines that we have currently. So, whenever you see DOS stub basically says the string this program cannot be run in DOS mode, right? So this basically explains to us that this program is not meant to be run in DOS on DOS machines as a DOS program. But in that particular flare-on challenge, once you solve the challenge, you basically got the string saying this program cannot not be run in DOS mode, right? So it was actually a DOS program. So this is the DOS stub can basically contain an entire program in itself that can run in DOS mode, right? Rich header. Now, rich header is really interesting because this particular header was discovered in 2015 and this was previously unknown. Now, Microsoft used this header in order to identify different malware groups that were using Microsoft tools in order to build their malware samples. Now, since this header was not previously discovered, they were not basically paying attention on changing the actual specifics inside this header. This header basically contains information about the compiler and the linker used to create a particular PE file, right? So this tells you a lot about what kind of tools were used in order to create a PE file. Microsoft was using this header to basically identify different kinds of groups from the malware samples that they collected, right? So this was a really good, you can say, signature detection mechanism that Microsoft was previously using. As you can see, it contains the rich ID and the checksum. So it's important to understand that there are several different checksum values that are present inside PE files. So these are actually the tripwires that are present inside PE file. So if you actually make changes to a PE file, it is important to change each and every checksum that is affected, right? Otherwise, you will basically make changes that could be easily detected by any endpoint detection system. So the PE signature. This is where the actual PE file begins from. It basically contains of these particular 4 bytes, PE followed by 2 nulls. So this is where the actual PE file begins from, right? Now NT header. NT header consists of file header and optional header, which in turn points to the data directories, which are the metadata of the sections present inside a PE file. File header. Now file header consists of machine type, number of sections, time and date stamp when this particular file was compiled, pointer to the symbol table, number of symbols, characteristics of the PE file. Now, how many of you all know what UWP stands for? UWP. What does it mean?
Universal Windows Platform.
Exactly. So, if you know what Universal Windows Platform is, basically Windows is trying to introduce a common API that can be used across all its different machine types. So, ranging from Xbox to Microsoft phones to Microsoft laptops and computers. So, this common API can be used to develop programs that can run on all these platforms, right? So, in order to have something like this, in order to have this ecosystem, it is important to make sure that your file format can adjust to each of those machine types, right? So machine type basically specifies the type of machine on which this particular PE file is expected to run, right? So these are basically some of the characteristics that are present. So it can be like whether it's an executable image, whether the relocation symbols have been stripped, or whether it's a 16-bit machine. So there's a ton of information that is contained inside the file header. Now, time date stamp. Who knows what January 1st, 1970 means? Exactly. So, any time and date stamp that you have that is present inside this particular field is basically a time delta from that particular timestamp, right? So, this basically helps you identify when this particular binary was compiled. Now, the funny thing about this is several different time date stamps are present inside PE files, right? There are several different time date stamps that are present. So it's not just enough to change the time date stamp that is present in the file header, right? You need to change each and every time date stamp that is present inside a PE file. So this is a relatively important field. Now the optional header. Optional header, even though it says it's an optional header, it's not really optional. It contains a ton of information, a ton of important information that you need in order to execute a program, right? So it contains the base of the code, which points to the text section where the actual code is present, right? It contains the main subsystem information, version number, operating system information. So it basically it contains a ton of information which is not really optional, right? At the end of the optional header, there is a data directory table which is present, which points to the actual data directories that are present inside a PE file. So these are some of the data directories that can be present inside a PE file. Not all PE files have all these data directories, but some of them, like import, export, those are some of the common data directories that will be present inside almost every PE file, right? So we'll have a look at some of them and what they mean. So export table. Export table basically points to the .edata section inside a PE file. Export table basically contains information about all the functions that are exported by this particular PE file. Now, as some of you may or may not know, a PE file can be a DLL or an exe, right? So DLLs are basically dynamically linked libraries, right? Now libraries do not really execute functions on their own; they export functions that are used by different PE files, right? So DLLs will most probably have an export table which is very large, which contains a number of functions that are exported by that particular DLL, right? Then there is the import table. Now, exactly opposite to this, normal EXEs are basically programs that are meant to import functions from different DLLs and run those functions, right? So import table contains those imported functions. Now, for an EXE, it will have a large number of import functions, so the import table will be larger than the export table. Resource table. Now, if you know, programs are not just meant to be run on CLI, right? Programs can range from anything from games to music players to a ton of different things which have graphical user interfaces, right? Now, all that graphical data needs to be stored inside the PE file. Now, that data is basically stored inside the PE file and pointed to by the resource table, right? Resource table contains addresses of all the resources that are needed in order for that particular PE file to run, right? So if you have a .rsrc section, that basically means that you have a ton of different resources like icons and dialog boxes that are present inside the PE file. So if you go through the resource table, it is basically a very easy way to find out whether a particular program is a GUI or a CLI, right? Exception table. Now, for good programming practices, programs have exceptions, right, that need to be handled. Now, how those exceptions will be handled needs to be stored inside the PE file. Exception table basically contains the pointers to the exceptions and the functions that trigger those exceptions, right? This is really important because you may have edge cases that need to be handled by these exception handlers, right? So the exception table basically contains all that data. Certificate table. Now, how many of you all know what a certificate table may consist of? Yes.
Contains the sign authority for that program, like this is signed by Apple, or you should run it.
Exactly. So if you have downloaded any program that is not from Microsoft and try to run that, you basically get a dialog box saying that this program is not being issued by Microsoft, right? That this table is what causes that exception to occur, right? Because if a particular program is not signed by Microsoft, it tries to tell you that this program may or may not be malicious in nature, right? So if you have, say, the signing certificates for Microsoft, you could basically sign a malware and deliver it to anyone, and they could basically run it as a Microsoft-based program, right? And there would never be an exception, right? So this is a table that you can utilize to change the certificate of a particular PE file. Debug table. Now, debug table is usually stripped for all the commercially available PE files because most companies don't want you to know the debug information of a PE file, like what kind of breakpoints were used in order to debug this particular program or what kind of debuggers were used. So this table is usually stripped, but if it's present, it usually contains the debug information that pertaining to that particular PE file. TLS table. Now, how many of you all know what a TLS table could stand for? It's not the TLS for networks, so what could it be? So Microsoft, like any normal operating system in today's world, has multi-threading available to it, right? So TLS basically stands for thread local storage. So a particular program, if it's running, if it has multi-threading capabilities, a same variable can be present in multiple different instances of that particular program, right? There can be multiple different threads utilizing different values for same variable, right? Thread local storage basically stores all that information, right? It stores multiple instances and instances of a variable and data present inside a PE file. Import address table. Now, import address table for most part is same as the import table before the file is run. But once the file is loaded in memory, import address table basically changes to contain all the symbols and all its actual addresses present inside the DLLs from which those symbols were imported. Right. So once it is loaded in memory, once the PE file is loaded in memory, import address table becomes really important to see. Now, all this is followed by the section header, which is the metadata for the sections present. It contains the name, the virtual addresses, the size of the raw data, pointer to the raw data, and characteristics of a section header. Now, can anyone tell me why characteristics of a section might be important? Why it should be relevant? Like, it's just a stream of bytes, right? Why do you need to specify characteristics of a particular section inside E file? Like, what good could it do? Anyone? So basically, any section, like code cannot be run from any section present inside a B file, right? You need to specify permissions and a ton of other metadata for a particular section, right? Not all sections present inside a B file are runnable. Not all sections have the execute permissions. Just imagine if every section present inside a B file had execute permissions. What you would have is basically you would have to have checks for each of those sections. Like executable code could be present in data, executable code could be present in iData. Not all sections require execute permissions, right? You only need execute permissions for the sections that have code that needs to be executed, right? All that data is contained in the characteristics field of the section header for that particular section, right? So now that you know what a PE file looks like and what are some of the basic things and basic data structures that are present inside PE file, let's move on to the current code injection techniques for any PE file, right? So the most common code injection technique that is present for any PE file is custom section addition, right? So once you have the entire PE header followed by the actual sections, you basically just add another section and have that present. Like in that section you inject the malicious code that you need to execute, right? And then you redirect the entry point of the function to point to that particular section which has the execute permissions. Now can any one of you tell me what problem could a person face if you do like PE file injection in this technique? Like what could be some of the problems that you could face? Like why is this not doable?
Checksum could change.
Say you change the checksum to accommodate this change. Yes.
Wouldn't the control flow doing that be like a red flag for an hour?
Okay, close enough. So if you redirected the control flow to point to something that is not part of the actual execution flow, that could be a red flag. But even before that, like you wouldn't care about that because your malicious code has already executed, right? So what could be one of the major red flags for this particular thing? Like for this particular method?
Trying out to access memory that's outside our address space? Or
No. So like as I said before, if you add another section and you want that code to be executed, that section needs to contain execute permissions, right? Now for a benign PE file, the only section that usually contains execute permission is the .text section. So if you have a section that is present inside a PE file that contains execute permissions, that is an instant red flag. Like I don't even need to run this PE file. I can just look for like which sections contain the execute permissions, and if that section does not belong to one of the normal sections that you have inside a particular list, you can just say that this particular file is malicious and you can send it to a sandbox, right? So that is one of the reasons why this approach is not viable. The stealth gained using this approach versus the time required for its correct implementation is way too low. Like you gain very little stealth for the amount of pains that would be required to go through this approach, right? You can't just add a section at the end of the PE file and expect it to run. right? You would have to change the section headers, you would have to change all the checksums, you would have to change the time date sum. So it's a ton of different things that you have to do, and in the end, it would be easily red flag, right? So this approach is not really viable. PE code caving. Now in this technique, you look for code caves. Now can anyone of you tell me what code caves are? Yes.
Parts of a PE that have null bytes or sections that are identified as not being used.
Exactly. So a PE file can contain like a stream of nulls inside its. So PE file is basically a stream of bytes, right? In the end, it's just a ton of bytes that are present in a particular format, so it executes. So there can be a stream of nulls present inside a PE file which is not being used by anything, right? So that space can be used to accommodate our malicious code. And here we are not adding another section. We are not doing any of the additions. We are just using space that was previously not being utilized, right? So we add malicious code to that to the code key present inside a PE file, and then we basically redirect the flow to point to that particular code key. Now, what can be the problems you can face while you're trying to code key a PE file? Like, why is this technique not viable? Looks pretty fine to me. Like, you're not adding another section, you're just using like section that was not like part of a PE file that was not previously being utilized. Why is this not viable? That's one of the reasons. There might not be enough space. Yes?
It's not guaranteed for each executable you find. It's going to be inconsistent. You're going to have to scan it every time.
You might have a PE file that might not contain PE code caves. So this is one of the common techniques that could be used to prevent code caving of PE files. You could just have random garbage data present at the code caves that are present inside your PE file, and then there would be no code caves, right? You wouldn't be able to differentiate between a code cave and normal data because there's no stream of nulls, right? One more reason. Yes. Okay, that's common, but that you'll have to edit for each and every like PE injection technique, right? So if you want to code cave a PE file, you have the same problem as mentioned before, right? The code cave needs to be present inside the executable section of a PE file, right? You can't have your code cave being present in any section of a PE file. So the constraint are you need to have a big enough code cave to accommodate your malicious code. The code cave firstly needs to be present, and it needs to be present inside the executable section of a PE file. Now, these constraints are usually never accommodated by any PE file, right? So, this technique, even though it's really good, it cannot be utilized. Like it has a really huge miss ratio, right? So, why can't we just edit the .text section of a PE file? Like, why not? Let's just take the code that is present inside the text section of a PE file and edit that text section. Like, what could be the problems that we could face if we wanted to do that? Like, the text section contains all the code, and we need to add to that code. So, why not just do that? What could be the problems that we would face?
It doesn't work anymore.
That could be one of the problems. Say you got it to work. Like, what would you have to change?
It doesn't have its original functionality, so it should be easily detected.
Huh. Okay, but like even before that, like if you say you made sure that the original functionality stayed the same somehow, and you had like you could basically injecting into text section was viable. What could be the problems that you could face even before that?
Wouldn't you have to change all the other addresses of all the other sections?
Exactly. Right? Because the text section is usually the first section that is present after the section headers. So if you change the text section, each and every addresses and everything basically that comes after it needs to be changed, right? So that's a huge amount of work, right? So what would you need to have in order to do something like this? Like what would you need to have?
Something template the execution and see where all the addresses, see what all the addresses really are. See what numbers really are addresses.
Exactly. So if I had to summarize what he just said, you would basically need complete control over your PE file, right? You know what goes where, you know how addresses work, they basically need to have complete control over each and every data structure that is present inside a PE file. You need to change import tables, you need to change addresses inside those tables, you need to change a ton of different addresses inside .data section. You have to change basically a ton of different stuff, right? So you need something that could allow you to have access to all those different data structures and the virtual addresses, right? So this is basically what Perfidious aims to do, right? Perfidious basically parses the entire PE file and it parses each and every structure that is present inside a PE file, and then it performs all the recalculations for you, right? So what it does is basically it takes your text section that is basically just a bunch of bytes, converts it into the assembly code corresponding to that text section, then it performs injections in between the text section so that the original functionality of a GUI is not interfered with, right? The original functionality remains the same. So basically you have changed the size of the text section. So then the next thing that you need to do is change all the addresses that come after it, right? So that is what it aims to do. It basically tries to control each and every aspect of a PE file so that you can alter it in the way that you want it to, right? So the advantages of this approach is it would be really difficult to detect it statically, right? Because it would have almost the same functionality of the regular PE file. The entropy wouldn't be changed because the entropy of the text section the text section would be the only section that contains the code, right? So the entropy of the PE file would be relatively same. The malicious code itself is divided into smaller pieces and injected into the control flow of the regular program, right? So you have jumps that are present that link to the malicious code. So when you execute it, then that is the only time that the malicious code would be executed, right? So this is something that I and my friends are trying to do. And how would you detect something like this, right? The easiest approach to solve all these problems is basically only allow whitelisted software on your network. Now that is not really viable, is it? Because it's not something that is really possible. Another approach is performing dynamic analysis on each and every PE file that is passed through your network. Now, that is something that can be done if you have a proper endpoint detection system that is running on your network and performing all those things for you. But it's not something that contains speed, right? Because each and every PE file that is passed through your network will need to be dynamically executed inside a sandbox, right? So the third approach is something that I found out while I was presenting the same thing at Singapore. A group of researchers is currently working on a technique that could be used to create a graph hash for the control flow graph of a program, right? You insert a PE file and it creates a hash for the control flow of a program, right? So if your control flow hash is basically different from the hash of the original program, you could easily say this program performs something different from the original program, right? So this is one of the things that could be easily used to detect this kind of injection technique. Now, Perfidious is currently under development, but I would just like to show you a peek into how it does something. So Perfidious basically creates a class file of the entire PE structure, PE file that you pass into the Python program, and then you could just say print demo, and it will basically show you some of the right? So what it does is it tries to parse through the entire PE file and identify all the structures that were found or not found inside the PE file, and then it creates the PE object which is present at that address. Now this PE object basically contains all the individual data structures inside the PE file, so you can access that data structure as subclasses of the PE file, right? So you could say, I want to see the DOS header of this particular PE file. So if I run that, it will basically print the DOS header and all the hashes that for that particular DOS header. Now, how are those hashes really useful to you? Like, how could those hashes be used? Anyone? Like, why would you need intermediate hashes? not just for DOS header, but for any data structure inside a PE file. Why would you need intermediate hashes?
So you can narrow down what sections to change.
Exactly. Or for a particular malware family, what sections are basically being used in order to contain the malicious code. So it basically allows you to pinpoint exactly what is changed in between the malware malicious file and the PE file. Right now we are using import hash, right? What import hash is basically a hash of the imports that are being done by a particular PE file. That is used currently in order to detect malware samples, right? It is good enough, but it only works on the, it only functions based on the import hash of a particular PE file, right? What if I imported a function and never used it, right? The import hash would be different for that PE file. So this can be used as a much better hashing mechanism in order to detect changes between PE files. So as you can see, print function uses just like the normal. You can use print function just like normal Python in order to print various data structures that are present inside the PE file. Now, just parsing the PE file and having the ability to read those structures is not enough, right? You will need the ability to change those structures that are present inside PE file. Now, this is a demo of that one of the data structures being changed, right? So what I'm doing is basically I'm first printing the original DOS stub that is present inside, like the message of the DOS stub that is present inside the demo PE file, which is putty.exe, and then I'm changing the DOS stub message to shellcon 2019 and then printing that, right? So in this same manner, this same thing could be applied to each and every data structure inside a PE file. What you would have at the end is you would have complete control over each and every data structure inside the PE file, and you would have relationships between those data structures, right? So say you would if you would change the message of the PE file structure, right? You would get like equivalent, like the checksum of the PE file would change, the data stamp of the PE file would change on itself. That is what we are trying to achieve, right? Maximum control over the PE file so that you have the ability to change it as much as you want. Once this is done, we come to the future of the project, right? So our goal is to basically complete the parsing and the editing of a PE file by December. Once that is done, we'll basically move forward to establishing the relationships between various data structures, and then we would have a good enough knowledge of the Windows loader that is used in order to execute the PE files. The next step for this project would be to develop a machine learning algorithm that could automatically change data structures inside PE file to closely resemble malicious samples. This could basically be used to identify new methods of code injection inside PE files. So that is what we are trying to do. Thank you for your time. Any questions?
Is there early versions of this available online yet?
So since we are developing this under Cybrary, it's a corporate thing. I will be releasing, like it's online, but it's a private repository right now because it has not reached a version which can be released. So by December, we aim to release an alpha version of this particular library. At that time, it will be available to everyone to explore, but currently no. Since like we cannot release incomplete project under a company. So
When it is ready to release, what platform or account will it be under? Do you know?
So this entire project is being developed under my own personal GitHub account because Cybrary itself doesn't want to use this under their GitHub account. So yeah. This is the GitHub account under which it will be available. Xbuilder. That's me. So yeah. Just a shameless plug. I'm also looking for full-time cybersecurity positions starting May 2020. So if you think this kind of work is something your company wants to do, please let me know.
It should be.